Hello everyone, myself Jenny Solanki and today I am going to present my views on one of the most popular processors in the computing world, that is Intel Core i5. This processor belongs to the Intel Cores family for making it ideal for everyday computing, gaming and even professional tasks. The first slide is an overview of the Intel i5 family of the processors. The Intel i5 family is a popular mid-range CPUs known for their balanced performance and power efficiency. It offers a solid combination of cores, threads, and clock speeds to handle a wide range of everyday computing tasks, and it increases automatically the clock speed whenever needed and thus increases the efficiency and performance. 2009, first generation of Intel Core i5 was launched and it was based on 45 nanometer and 32 nanometer process up to 4 cores and 4 threads. In 2011, second generation was launched and it was of 32 nanometer process again with higher graphics and better efficiency. Gradually and eventually, the more generations were launched and every time with a more better approach and shorter nanometer process. And finally, we have 14th generation available till date, which is considered best CPUs in market to build a mid-tier PC for gaming and many productivity tasks. Okay. So the general architecture of Intel Core i5 processors has evolved over multiple generations, but there are key components and technologies that form the backbone of this design: cores, threads, and clock speed. So, Intel Core i5 processors typically have between 4 to 6 cores. Each core can process has its own set of instructions, allowing for true multitasking. Its hyper-threading technology allows each core to handle two threads simultaneously. This increases parallelism and improving performance. Core i5 processors typically have three levels of cache: L1, L2, L3. L1 being the smallest but fastest, and L3 being the larger and shared among all cores. Cache memory helps to store frequently accessed data and instructions, reducing latency and speeding up processing tasks. And we will be discussing more on cache memory in the later slides. Newer i5 processor also supports PCIe 4.0 and 5.0 for faster data transfer. Exploring Intel i5 microarchitecture. In terms of microarchitecture, it reveals the intricate design and technology that powers its performance. Skylake. It is introduced a new CPU core designed and improved 40 nanometer process. Skylake is from 6th generation. Then the next is Coffee Lake. Coffee Lake belongs to 8th generation. It is utilized an enhanced 14 nanometer plus node and increased core counts. The last one is Comet Lake. It is from 10th generation. It brought up to 6 core and 12 threads in i5 lineup. In essence of microarchitecture, the Intel Core i5 balances performance and efficiencies utilizing advanced techniques like pipelining, branch prediction, and multi-level caching to ensure smooth and fast data processing across various applications. Multi-core design and hyper-threading. Parallel processing, hyper-threading, and the last one is scalable performance. Parallel processing in Intel Core i5 processors is one of the key features that significantly improves performance by allowing multiple tasks to be processed simultaneously. Some Intel Core Some Intel Core i5 models support hyper-threading, which enables each physical core to process two threads simultaneously. This doubles the number of threads the CPU can handle, improving the processor's ability to manage multiple processes efficiently. For instance, a 4-core i5 processor with hyper-threading can handle 8 threads at once, effectively boosting multitasking and performance in applications that support parallel computing. Turbo Boost, dynamic performance and scaling, adaptive clocking, thermal monitoring, and power optimization. Dynamic performance scaling in Intel Core i5 processors refers to the ability of processor to adjust its performance based on current workload and power requirements. Turbo Boost allows the processor to dynamically increase its clock speed beyond the base frequency when the workload demands more power. This increases in clock speed provides extra performance and reduces the load on processor. Moreover, Intel speed step technology helps prolong battery life in laptops and reduces the power consumption on desktops without sacrificing performance when it is needed. Adaptive clocking automatically increases clock speeds when a workload demands more performance. Thermal monitoring. It monitors the temperature and power consumption to enable safe turbo boost scaling and to prevent overheating. Power optimization is again turbo boost intelligence power to deliver maximum performance when needed. So, dynamic performance scaling is a multiple combination of multiple technologies like turbo boost, speed step, C states, and thermal management, ensuring that high performance is available when needed while conserving power and managing heat during lighter tasks or idle periods. Cache hierarchy L1, L2, and L3. In Intel Core processors, it plays a very critical role in enhancing processing speed by reducing the time it takes to access data from the main memory. The cache hierarchy consists of three main levels L1, L2, and L3 caches. Each level is designed to store frequently used data and instructions with varying size and speeds. The processor, when it tries to find out the data from the memory, it first tries to find out from the cache memory. If it gets the data from there only, that is known as cache hit. And then, whenever the data is not found in that memory, the processor needs to search for the data in main memory, that is RAM, which is known as cache miss. So, when the processor needs data, it first checks the L1 cache. If the data isn't found, it checks the L2 cache. If the data is still not available, it moves to the L3 cache. Only after three cache levels are checked, then only it moves to the RAM, which is much slower than the cache memory. So the data is stored according to retrieve as fast it it should be retrieved as fast as possible. Integrated memory controller. Integrated memory controller. It manages the flow of data between the processor and the system's main memory, allowing faster and more direct communication compared to older architectures where the memory controller was located outside the processor on motherboard's chipset. In memory channels, the IMC support dual channel, that is DDR memory, for increased bandwidth. In memory performance, it tight integration between the CPU and IMC enhances overall memory throughout. The on-chip IMC reduces power consumption and creating a discrete memory controller. The direct access reduces the latency, that is delay in fetching the and writing the data to memory, improving overall system performance, especially for memory intensive tasks like gaming, video editing, and scientific simulations. Execution units powering instruction processing. It contains three levels: arithmetic logic units, load store units, and branch prediction. The processor fetches, decodes, and executes and retires instructions using various components and technologies. The first step in processing pipeline is to fetch the instruction from memory, then it retrieves instruction from cache or main memory. Once it is fetched, then the decode unit converts the high level of instructions into micro operations which are easier to execute and allows more flexibility. Once instructions are decoded, then arithmetic perform that integer and floating point arithmetic operations are performed, and then As soon as possible, it completes the task and executes the instruction. It takes advantage of instruction level parallelism, allowing multiple instructions to be executed simultaneously. This achieved through the use of superscalar architecture, where multiscalar execution units can process several instructions in parallel. Pipelining for efficiency. It contains four stages of pipelining: fetch, decode, execute, and write back. Instructions are retrieved from memory and placed in the pipeline. The pipelining process it improves the instruction through output and overall performance by breaking down the execution of instructions into multiple stages. The fetch instruction decodes into simpler micro operations that can be processed by execution units. Decode. The decoded instruction is executed. This involves performing arithmetic or logical operations or data transfers. They are broken down into constituent operations. The hmm, execute. The various execution units perform the necessary computations. The result of executed instruction is returned back to the registers and into the memory. And then advantages of pipelining are higher clock speeds and efficient resource usage. How branch prediction reduces CPU stalls. Branch prediction is a key technique in modern CPUs that anticipates the outcome of conditional branches in code. By predicting branch decisions accurately, the CPU can fetch the right instructions ahead of time, reducing stalls and improving the overall performance of the processor. Intel's instruction set architecture. It refers to the set of instructions that Intel processors like the Core i5 are designed to execute. It defines how software communicates with the hardware at the lowest level, including the types of operations a processor can perform, the data types it can handle, the register available, and the memory addressing modes. Intel's instruction set began with x86 of 64-bit architecture. It was generally introduced in 1978 with Intel 8086 processor. It is the dominant CPU of instruction set, providing backward compatibility with 32-bit x86 while adding 64-bit capabilities. In CISC architecture, instructions are often complex and can perform multiple low-level operations in a single instruction. CISC basically stands for Complex Instruction Set Computer. So it helps simplify programming at assembly level and it can represent what would be several instructions in simpler RISC architecture. It follows CISC design with large and flexible instruction set for diverse applications. Microarchitecture implements the x86 of 64-bit ISA, optimizing performance, power, and other key matrices. These enhancements allow for better parallel processing, vectorized operations, and improved security, making the Intel ISA one of the most advanced and versatile architecture of the modern computing needs. Intel's integrated graphics. It typically comes with integrated graphics known as Intel UHD graphics or Intel Iris Z graphics, depending on the generation of the processor. They are built directly into the CPU, providing basic graphical capabilities without needing a dedicated GPU. UHD graphics. Intel's baseline graphic solution offering basic 3D and multimedia acceleration. It is found in many Intel i5 processors, particularly older generations. It is designed for everyday tasks such as video playback, web browsing, and light gaming. The next one is Iris Graphics. It is a more powerful integrated GPU with enhanced performance for gaming and creating more high resolution topics. So it performs better video editing and more advanced gaming, not still a substitute for a dedicated gaming GPU. Iris generally offers significantly better performance than previous generations UHD graphics, making it suitable for light gaming, video editing, and content creation. The graphics can dynamically allocate power between CPU and GPU, optimizing performance based on the workload. The enhancement in performance and efficiency make them well suited for both everyday tasks and most demanding workloads. Power saving features. The first one is speed step. It dynamically adjustment of CPU clock speed and voltage to balance performance and power efficiency. Next is power states. It performs multiple low power states, allows the CPU to enter a deep sleep mode when idle. Thermal throttling, automatic reduction of CPU frequency to prevent overheating and maintain stability. i5 processors are designed with several power saving features that help improve energy efficiency, extend battery life in laptops, and reduce overall consumption in desktop systems. It adjusts the processor's voltage and frequency according to the workload demands. When the CPU is under light load, it reduces the clock speed and voltage to save power. Under heavy load, it scales back up to provide the necessary performance. It has several low power states referred to as C states, which allow the CPU to enter into a low power mode when it is not actively processing tasks. The deeper the C state, the more power the processor saves. This feature is particularly beneficial in laptops, extending battery life during idle periods. The processor can monitor its temperature and adjust its performance dynamically to stay within thermal limits. This may involve reducing clock speeds or entering low power states to prevent overheating, especially beneficial in mobile device where battery life is crucial consideration. Smart cache technology. It improves performance and efficiency by optimizing how data is accessed and stored within the CPU. Unlike traditional designs, when each core has its own dedicated cache, Smart Cache allows multiple cores to share a single cache pool. This means that when no one know that one core leads into the cache, it can be accessed by other cores without needing to retrieve it from the slower main memory. It reduces the latency for data retrieval, which improves overall processing speed and efficiency. The Hmm. The smart cache can dynamically allocate cache resources based on workload requirements. If one core requires more cache due to a heavy workload, it can be accessed by the other core. This adaptability allows for more efficient use of cache space. Intel Core i5 processors typically include multiple level of cache L1, L2, L3, which we already discussed in the before slides. By having a shared cache, the processor can reduce the number of times it needs to access the slower main memory, which speeds up the data processing. Accessing data from cache is more energy efficient than fetching it by RAM. By improving cache utilization, smart cache technology helps reduce the overall power consumption of the CPU. Security technologies. i5 processors incorporate several security technologies designed to protect systems and data from various threats. These technologies provide a layered approach to security, helping build a safeguard against malware, unauthorized access, and several vulnerabilities. Software guard extensions. Intel software guard extensions enable secure enclaves for running sensitive code and data, and they can be exposed to the rest of the system. This is particularly used for protecting cryptographic keys, personal data, and other confidential information. TXT, Trusted Execution Technology, provides a hardware based root of trust from system integrity. It verifies the integrity of BIOS and bootloader before loading to the operating system. This prevents the unauthorized software or malware from executing during the boot process. TXT can create a trusted execution environment that isolates the sensitive applications and data, providing a secure area for running trusted applications. Secure boot. It ensures only trusted sources. It prevents malware from loading during the boot process by verifying the digital signatures of bootloaders and operating system kernels. Also, there are many technologies introduced for security, as at every point security must be our first priority. Advan- uh, it is an also advanced topic that provides hardware based acceleration for encryption and decryption operating using the AES algorithm. This enhances the performance of the encryption tasks and improves the overall security of data at rest and in transit. Thermal design and cooling, these are the critical aspects of processors, ensuring they operate efficiently and maintain performance without overheating. TDP is the maximum amount of heat generated by the processor that the cooling system is expected to dissipate under typical workloads. They typically have TDP values ranging from 35 watt to 125 watt, depending on the specific model and its intended use. Understanding TDP helps system builders choose appropriate cooling solutions to prevent overheating, ensure stable performance. These coolers are adequate for standard usage scenario, but may not suffice for heavy workloads or overclocking. Most coolers use materials like aluminum or copper for their heat sinks, as these metals efficiently dissipate heat. Copper is often used for the base due to its excellent thermal conductivity. Features such as PWM, which is pulse width modulation, control allow fans to adjust their speeds based on the CPU temperature, providing quiet operation during light loads and increased cooling during heavy usage. CPUs, these sensor allows the processor to dynamically adjust its performance to prevent overheating. System interconnects. It uses various system interconnect technologies to facilitate communication between the CPU, memory, and other system components. These interconnects are critical for ensuring high performance, efficient data transfer, and overall system responsiveness. DMI is a high speed interface for communication with the chipset, and different generation of Intel uses different versions of DMI with improvements in bandwidth. For example, Intel DMI 3.0, it offers a bandwidth of up to 8 GT per second, while DMI 4.0, it often even it offers even higher bandwidth for data transfer. PCIe Express Link for connecting high-speed peripherals and expansion cards to the processor. Depending on the specific i5 model generation, it may support multiple PCIe lanes and allowing for higher data transfer rates. The memory bus is used for communication between the CPU and various components on the motherboard, such as temperature sensors, fan controllers, and power management ICs. These allows for monitoring and managing system and health and performance. PCIe connectivity. It provides high-speed communication between CPU and the peripheral components like graphic card, SSDs, network adapters, and other expansion cards. It was introduced PCIe 4.0. It was introduced in 11th generation, and 5.0 was supposed to be in 12th and 13th generation. It typically provides 16 PCIe 3.0 lanes for connecting high-speed peripherals. The lanes can be configured to support different device combinations and bandwidths. It enables the addition of graphic card storage devices, network adapters, and other components as well. Benchmarking Intel i5 processors. Productivity. Intel i5 processors demonstrate strong performance in office productivity applications, delivering fast response times and seamless multitasking. Gaming. With a balanced blend of processing power and energy efficiency, it offers an excellent gaming experience, especially in popular AAA titles. It excels at handling resource-intensive media tasks such as 4K video editing and rendering without compromising system responsiveness. Intel i5 processors in action. The first one is gaming. Smooth gameplay, fast load times, and immersive visuals make processors an ideal choice for enthusiast level gaming. The next one is productivity, multitasking, rapid application resource, efficient resource management enable Intel i5 to power through demanding productivity and workloads. And the last one is multimedia. Powerful video encoding, smooth playback, and hardware-accelerated media processing make Intel i5 processors an excellent choice for multimedia enthusiasts. Architectural challenges for Intel i5. The first challenge that can be is as Intel introduced higher core counts and faster clock speeds and more advanced features like PCIe connectivity, DDR5 support, it becomes increasingly difficult to uh, manage the power efficiency without sacrificing performance. The solution to it can be that they can use speed step and turbo boost technology to dynamically scale performance based on the workload, reducing power consumption during light tasks and maximizing power consumption when needed. The next challenge can be is thermal management, that it generates more heat, making thermal management a critical issue, especially in compact form factors like laptops or small desktops. Managing heat efficiency without thermal throttling is a significant of challenge. So for this, they can go through like architectural improvements such as enhanced cooling solutions and dynamic thermal frameworks. The last one is memory bandwidth. As core count increase, ensuring that the memory subsystem can supply data fast enough to all core becomes more difficult. Insufficient memory bandwidth or high latency can be more difficult. So that high latency can bottleneck the CPU, limiting its potential performance, especially in memory-intensive application. Intel has incorporated DDR5 support in its latest generations, which helps to reduce latency, but balancing bandwidth latency and cost remains a key challenge, especially for consumers and all of the users. The future of Intel processors. The first one is advanced process nodes. Transitioning to smaller and more efficient process nodes will be greater transistor density and energy savings. Next is heterogeneous computing and innovative architectures. Heterogeneous computing is like integrating specialized processing units alongside the CPU core will unlock new levels of performance and efficiency. Innovative architectures such as new design approaches, leveraging emerging technologies will drive continuous improvements in Intel processors lineup. We are done now with covering all the topics related to the architecture of Intel Core i5 processors. And thank you everyone for watching.